This video discusses system response. Alright, so we've already talked about closed loop systems, and we know that closed loop systems are dynamic systems. They're going to respond to a change in a set point, and they're also capable of responding to outside disturbances because the process variable, that's what we're calling PV here, the process variable or the process parameter that we want to control is being fed back into the controller, the PLC, and we're going to set a control output in response to the error. Right? So good control systems must meet three major control objectives. They need to provide the desired transient response. They need to reduce steady state error, and they must provide stability. To achieve any type of control system, we have to consider the performance and the cost of the system and also the system robustness. Alright, so when we start talking about how the system is responding, we basically break it down into two parts. What we call the transient response, which is due to changes in the set point or disturbances. And the steady state. So it's a steady state where we're at a point where we're going to maintain this value until either a disturbance comes in again or we have a change in our set point. Okay, so the transient response is how the system reacts to a change. And so when we look at this is actually a first order system here. So we have the process variable versus time. So the whole point of transient is we're looking at how it's going to change over time. All right, and so when it changes, you can see the example here on the left side. This is a very slow change. This is what we call an overdamped response. It's very slow and it takes a long time. So this the black line here, horizontal black line, indicates the change in the set point. So we had an immediate change in the set point, which we usually refer to as a step response, and then we had the process and then we had the blue line then represents the system slowly changing up to that new set point. Now in the second example here, we actually see some oscillations. What's happening is the system is responding very, very fast, and it's actually overshooting the new set point, and then it's overreacting and it's bringing it down below the new set point, and then it's going above the set point again and then back below until finally it settles out to the set point. So the example here on the left is what we call an overdamped system. It's a very slow response, and the example on the right is what we call underdamped. And so we get a fast response, but we have a lot of oscillations and overshoot. All right. The steady state then refers to when the system has stopped changing. And so it's if the set point is solid, as the red line there is marking the set point on this slide, and the set point has been changed and is no longer changing, then the system eventually is going to reach what we call the steady state. Now, what we can one of the big things we look at considering the steady state. Once the system's not changing anymore, the question is did it reach the set point? Right? The red line here indicates the set point, and in neither of the two cases shown did the blue line, which is actually the process variable, reach our set point. Okay? So that generates what we call a steady state error. All right, so there are four desired conditions or values that we want to look at when we're trying to analyze the system. Okay, so number one was we want to be able to define the type of transient response, whether it's overdamped or underdamped or critically damped. We'll look at those in detail a little bit later. And then the length of time. How long does it take for the system to respond to that change in a set point? Okay, that's the transient response. How long is that transient response? And then the steady state, is the final value equal to the set point that we set, or is it above it or below it? All right, so this is an example here where we have the process variable of basically three different systems here. So we have the green line is what we call an overdamped response, so it's a very slow system. The red line is what we call critically damped. Okay, the red line is showing what we call as a critically damped system, and you can see that it rises up to its final value of 1 in this case. So it rises up to 1 and then it stays there. It doesn't move. So this is an example of a critically damped system. And when it's critically damped, what that means is it's going to rise up to this set point value, or at least to its final value. It may not actually reach the set point, but it's going to rise up to its final value as quickly as possible with no overshoot. Okay, so it's going to rise up as quickly as possible with absolutely no overshoot. Now the blue line, on the other hand, is underdamped. And so you can see, actually it's interesting when you look at the blue line. If you look at the blue line down here, it's actually behind the red line. So it's actually taken a little bit longer to get started. That's because the system actually has more inertia in the system. And so it's taken a little bit longer to get started. But once it gets going, it actually ends up getting right up to here, which is our final value. It reaches the final value faster than the critically damped system did. However, it's going so fast and it has that extra inertia in it that it's actually overshot the final value by, looks like a 70% here. So it's got actually, I don't have the value marked there, but it's got something like about 70% overshoot. It's supposed to go to 1 and it's going to 1.7. So it's really surpassed the system. That inertia in the system is taking a long time. That the control system is now trying to slow it down. Finally, at this point, the control system's got it turned around and is moving back. But then at this point now, it's that inertia's in there again, and the system is actually driving it too hard, and it actually now goes back below that value, and it oscillates back and forth before finally disappearing. All right, so as we already kind of discussed here, we have for transient responses, we have three types of systems. We have the overdamped, the critically damped, and the underdamped. All right, now an overdamped system acts like a first order system. It may not actually be a first order system, but it's a system that has what we call one pole is dominating, and we'll get into more detail about how we figure out what the poles are, right? But if it's a critically damped, or excuse me, not critically damped, but an overdamped system, we have one pole is basically the slowest pole in the system, and it's pretty much dominating everything else. So that's an overdamped system. Now, overdamped systems uh, sometimes are very good. Sometimes you don't want the system to be moving too fast. An example would be if you think about you have a large ship like a one of those great big cargo ships or aircraft carrier or something, and you're bringing it into dock and you're going to dock it. You can't have it running overshoot. Overshoot would mean you ran into the dock and destroyed the dock before you got back away from the dock. Okay, so overshoot would be really bad in that example. So you have to have an overdamped system for something like a ship coming into dock or something like that. You can't have any overshoot. And so you don't even want it to be critically damped, because chances are that if you're a little bit off, you have a little bit of overshoot, which means you actually crashed into the dock and are causing damage to the ship or the dock or both. So, at times you definitely want a severely overdamped system. All right, so uh, for oscillations, or for a critically damped system, you need to have at least a second order system. You could have more than a second order system, but you must have at least a second order system. To get critically damped, what that would mean is that the two poles are exactly the same. And again, we'll get into how we calculate poles and how we can look at a pole and see what's happening. But the two dominant poles exactly equal will effectively give you a critically damped system. An underdamped response is going to give you the oscillations. All right, and when we start looking at poles, you'll see that if the system poles actually become complex or have a imaginary component, then we will get oscillations. Now, the time response, when we look at the time response, we want to, number one, we're going to have to kind of define a couple of aspects of that so that we can always be talking about the same thing. Okay, so if we want an overdamped system, like a crane would be another example of an overdamped system, where you need the system to just respond slowly and smoothly. You can't have it oscillating back and forth. Could cause damage or injury. All right. So when we start talking about the time response, there's three things that we talk about usually. One is called the dead time. The dead time is the amount of time it takes for the system to actually begin changing after the set point has changed. So you see here at time t equals 0, in this we have t equals 0. Okay, right here at time t equals 0, the set point immediately jumped between 0 and 1. So again, this is what we call step response, when it steps up. So there's an immediate step. It's not a gradual change. It's an immediate step. So at time t equals 0, there was this immediate step where the set point changed. But the system can't change that fast. All right, and so the dead time is the amount of time it takes for us to even see the system start to respond. Now, part of that dead time could be, and is if we're using the PLC, is due to the delay within the PLC. I mentioned that in a different lecture, that there's an automatic built-in to the scan of a PLC. So even if you're sending out the control every scan, there's at least maybe a millisecond of time for each scan to execute. And so at the beginning of the scan, we read values in, we read in the new set point, but then we got to run through all the ladder logic, and then we got to generate our control output and then actually send it to the output before we see a change. So the dead time here is, like I say, part of that dead time is simply the fact of the scan time of the PLC, or the control loop of your controller. But there are other aspects of the dead time, is like if you're moving gears, or trying to run something with a chain, there's slack in the chain or things like that you have to kind of tighten up that before you actually see the system response. So there's some mechanical effects for dead time, and also there's some built into any digital computer response. Alright, so now once the system starts moving, we want to analyze the rise time. Alright, so once it starts moving, we'll talk about the rise time. Now, to be consistent, we discussed the rise time as being the time where the trace crosses 10%. So you see it's going to 1, so this line here is 20%, right, 0.2. So we're looking at 0.1. So where the process variable crosses the line of 10% of its final value. Now, it may not be the set point, but it's the final value. In this case, they're one and the same, but later on we'll look at responses that don't make it to the set point. But when the value crosses 10% of its final value up to, and first reaches 90% of its final value. Now, it may actually overshoot and come back below that 90%, but the rise time is defined as when it first crosses the 90%. So between 10% and 90% of the system's final value, not the set point, but the system's final value. That is the rise time. So we can talk about basically how fast it's taking for the system to get within 10% of its final value due to the change. Right? And then the third time that we look at is called the settling time. And the settling time, what we want to look at is how long it takes to settle. However, if the system's bouncing around a lot, sometimes it's kind of hard to determine that. So we define that as being within 10%. And I'll show that on a different graph here. But it needs to be within 10% of the final value. All right, pretty much talked about the dead time. This is talking about the 10 to 90% I just mentioned. All right, and then the process variable within plus or minus 10% of the final value is the settling time. All right, so I'm going to jump ahead to a different slide here for a minute, and then I'll pop back. It's further ahead than I thought. All right, so I just want to show you here. Here is an example of it's bouncing around, and so when we try to calculate the settling time, what we need to do is we need to look at it between 90% of the final value and 110% of the final value, plus or minus 10% of its final value. And so that the time where it first crossed 10% until it gets within these two black lines here and stays, that's the settling time. Alright, so this is an example of where it's bouncing around a lot, and so we're just going to call it We're going to call this the settling time ending right here at this point where the response gets within those two black lines. It may still bounce around for quite a while, but we're going to call that the settling time. Alright, so when the system is bouncing around a lot, or maybe it's a over damped system and not bouncing around at all, well, that is basically due to something we call the damping coefficient. Alright, so if it's bouncing around a lot, what that's saying is there's not much friction or resistance in the system. The system can just sway back and forth due to just a little bit of a push from either the set point change or from a disturbance, and the system can start swaying around very, very easily. Or the system is has tons of resistance or friction if it's a mechanical type system, and it can't move very fast, and when it does move, there's lots of friction slowing it down. So anytime you try to move it, it's got all this friction in the system. Now, so what we call the damping coefficient is basically a gauge of how much resistance is in the system due to the nature of the system to oscillate. Alright, so for zeta to actually exist, we're assuming we have at least a second order system where we have two different factors that are going to push the system that are kind of going to oppose each other. Alright, so if our damping coefficient is greater than 1, it basically says we have lots of damping, lots of friction, lots of resistance in the system. Alright, and so the system is going to be over damped. If the value of zeta, this here, the damping coefficient with this symbol is with the Greek symbol zeta, Z-E-T-A, zeta, that's what that symbol is. But if the damping coefficient zeta is exactly equal to 1, that means that the system is critically damped. It means that the system is going to rise up to its final value without any oscillations, without any overshoot, as fast as it could possibly go. So that is the zeta equals 1. And if zeta is less than 1, then the system is under damped, and you're going to have overshoot and oscillations in the system, meaning there's very little resistance. Alright, so where do we get these when we start talking about a second order system? Alright, if we think about a capacitor, we know that a capacitor stores up charge in an electric field. And so capacitors don't like you to change the voltage. But on the other hand, over here we have an inductor. And inductors, they don't like changes in current. And so this inductor and this capacitor effectively oppose each other. One doesn't like changes in voltages, and the other one doesn't like changes in current. And so these two opposing sort of circuit elements give us those oscillations. If we have just an inductor and a resistor in a circuit, or just a capacitor and a resistor in the circuit, then we're going to have what we call a first order system, which, if you remember, is an overdamped system. You can, with just a capacitor and resistor, or just a inductor and resistor, you cannot have any overshoot. The system will not overshoot because there's nothing to build up that inertia. Alright, so what happens with an RLC circuit, as we have here, when you first set the switch, the inductor doesn't like changes in current, so it prevents the current from moving very fast. But then the capacitor, on the other hand, is trying to get the current to move as fast as possible. And so what happens is we get current flowing, and once we get current flowing, the inductor doesn't like you to slow it down. Okay, it's not that inductors don't like current, they don't like you changing the current. So once you get the current going high, the inductor wants to keep it going high. So when you try to slow it back down, the inductor keeps pushing. And so what happens is, when you have an inductor and a capacitor in the circuit, they sit there and basically give you this oscillation. You end up charging up the capacitor, but once the capacitor starts getting to full charge, it says, I don't want any more current, so it tries to stop the current. But the inductor's like, no, I don't want you to stop. And so the inductor keeps pushing extra current into the capacitor, and it basically fills it up higher than it was expecting. And so therefore now the capacitor is going to dump that back off and flow back the other way, so you get current flowing the other way. So these two are kind of like a seesaw here, passing energy back and forth in the system. And the only thing slowing it down is the resistor. And so the resistance in there, the more resistance, the slower the system will be. All right, now in this case, I have a resistance of 100, which is quite a bit of resistance. Okay. All right, so as we go through here and we look, right, this is an RLC circuit. So if we wanted to find the voltage across the capacitor, we can do that, right? We can use the voltage divider rule to find that the voltage across the capacitor is equal to the impedance of the capacitor divided by the total impedance times the supply voltage. Right? That'll be the voltage across the capacitor. So now if you think about the equations for a capacitor, we have 1 over omega c. Now if you don't remember, omega is actually 2 pi times the frequency. Okay, omega is 2 pi times the frequency. And so we get this 1 over omega c is the impedance of the capacitor. And the impedance of the inductor is J omega L. The J is just, remember the J says it's a positive J there, which indicates that it's a, you know, the phase angle of your current, and this is a 1 over J. So remember remember that the current leads voltage in a capacitor, and the voltage leads the current in an inductor. So that's what the J is that 90-degree phase angle, but inside of the inductor and the capacitor. All right, so when we look at the total impedance, we see that the total impedance is R plus J omega L. Remember, omega is 2 pi times the frequency, so it's the angular frequency of the system. And then the capacitor, the reactance or the impedance of the capacitor. All right, so the total impedance is, of course, the resistance plus the impedance of the inductor plus the impedance of the capacitor. Now, so if we solve this for the voltage of the capacitor divided by the source voltage, all right, this is our output divided by the input, then we get this system right here, and this is what we call a transfer function. This transfer function describes how the system responds from the input to the output. And so this is just an impedance. You've done this 100 times in AC circuits, right? Calculating the voltage across the capacitor or some other element in the circuit. And that's all this is. This is just the voltage divider rule here. All right, but this voltage divider rule we call the transfer function. Now notice this has this omega in it. Well, it turns out that if you solve this in terms of omega, you end up getting this omega squared plus omega times R divided by L plus 1 over LC. All right, now remember, omega is a frequency, right? 2 pi f, it's an angular frequency. Now, the very interesting thing about this now is the fact that we can tell the natural frequency of the system is the square root of 1 over LC. You see how this has an omega squared? So actually the natural frequency in radians per second is the square root of 1 over LC. That's the natural frequency of the system. So we can tell effectively what frequency the system's going to oscillate if we don't have any resistance. Okay, so this natural frequency is assuming 0 resistance. And then because we do have resistance in here, it actually slows that frequency down a little bit because of the resistance. But we can get the baseline of the actual frequency of any oscillation. So if we went back and looked at these things oscillating, right? So if you look at like this blue line here oscillating, what frequency is that oscillating? Well, its natural frequency is 1 over LC. Okay, now what I mean by natural frequency is meaning that it wasn't actually decaying. So it's actually going to be a little bit slower than that, but we can get that from this same equation. We can get the true frequency of oscillation in there. All right, so but this is what we call a transfer function. Now if you notice in the denominator here, we've got 3 coefficients, right? So this is a polynomial in the denominator. It's omega squared plus omega R divided by L plus 1 over LC. And so it's a polynomial, it's a second order polynomial, which means that we can have oscillations. And this is what we call the transfer function. So if we look at this polynomial, you notice the omega squared, right? That's just got a 1 plus omega squared. And then we have R divided by L. And then we have this 1 over LC. And as I mentioned before, 1 over LC is actually your natural frequency. See that lowercase n there? That means the natural frequency that this system would oscillate if we had absolutely no resistance. And then we have this term which has that zeta symbol in there. Remember I mentioned zeta is our damping coefficient? That's the resistance. Okay? If your resistance is 0, that center term goes away and you end up with a perfect oscillator. All right? But if you have resistance, which of course all systems are going to have at least some resistance in them, then you're going to have this 2 zeta omega n. So we can calculate zeta. Remember, if zeta is greater than 1, it means we have a ton of resistance and the system will be overdamped. If zeta is exactly equal to 1, then it means that the system is critically damped and it's going to reach the final value as fast as you can make the system reach the final value without any overshoot. And if zeta is less than 1, you're going to have overshoot and oscillations. And those oscillations will be effectively this omega n frequency minus a little bit because of the resistance. All right, so just some algebra here. But when we look at this system, we talk about poles and zeros. Now, if you look in there where we saw omega n, Okay, if you replace omega n with s, then, or not omega n, excuse me, just omega. If you replace omega with an s, that's basically what this is. So normally they write a transfer function here in terms of h of s. So this transfer function, we have s, which is, you could basically replace that with the omega for the frequency there. But here we have a s plus 3 in the numerator and an s plus 3 in the denominator. So this right here, s plus 3 gives you a 0. This 0 would be a minus 3. And the pole, if you look at what makes, what makes this a 0? Well, if you put s equals to minus 3, then minus 3 plus 3 would give you a 0 in the numerator. That makes it a 0. On the other hand, a pole, what happens if you put minus 5 in this denominator, right? So you have minus 5 plus 5 gives you 0, but you're dividing by 0. So if you're dividing by 0, effectively the system is going up to infinity, right? And that's going to cause problems. And so a pole is a value in the denominator that would make the denominator go to 0, which would make the system basically blow up, go break, be destroyed. All right, and so now notice here that if s is a frequency, if s is equal to omega and it's a frequency, you can never create a negative frequency. All right, so if s is equal to minus 5 is what would make the system go unstable, but since we can't generate a frequency of negative, then that means that the system is actually stable. And so we can actually look at a transfer function and analyze whether it's stable or not by looking to see whether the value, whether a positive value of frequency could make the system go to infinity. All right, if a positive frequency can drive the system to infinity, then the system is unstable because the system is going to end up breaking. And so transfer functions, we can look at the poles and the zeros. Again, the poles are the numerator, the value of, or excuse me, of the denominator, the value of the denominator that would drive the denominator term to infinity. And the 0 is a frequency that would drive the numerator to 0. Which would, if you drive the numerator to 0, it says you're driving this system to 0, so the system is just going to stop, right? It's not going to be moving because you drove it to 0. It's just stopped. So zeros aren't dangerous, but poles could be dangerous. And we can analyze this. So here is our RLC circuit that we were looking at before. And so this is the transfer function, right? 1 divided by LC is in the numerator, which means that it doesn't actually have a 0. There's no frequency that's going to make the numerator 0. It's always just 1 over LC. There's no S term there. But then the denominator has the S squared plus R over L times S plus 1 over LC, which is the natural frequency squared. Now remember, S could be any frequency that we want to push the system at. If you think about pushing someone on a swing, all right, you can push them and you can push them fast or push them slow, kind of thing. S is the frequency where you're actually pushing the system at. And 1 over LC is the natural frequency of the system squared. All right. So they're, you know, this is the frequency that the system is going to oscillate at if we had zero resistance. That, well, this is the square of that frequency, but looking at a system, we can see that. So now if we take the denominator of this, remember the quadratic formula from algebra class? And if we take and look at that, we have a squared plus bx plus c for the quadratic formula here. And if we have the s squared, that x, and should have probably used x in the, or s in this, but this is just showing you the form for the quadratic formula. And so if the a term is a 1, which is what we typically do on our transfer functions, we arrange it so that that term's a 1. But the b term, we have the b term here, and then the c term. Now, if minus 4ac is bigger than b squared, then that means that the system is going to oscillate. All right, so remember, c is that omega n squared. B is that B has that damping coefficient. It also has B is 2 times zeta times omega n. All right, and so the zeta, that damping coefficient, is in there. So we're saying basically if the damping coefficient is bigger than 1, then this system will not oscillate. And if that's the case, you're going to have these red dots. You're going to have these red dots here, which are what we call overdamped placements of the poles. So remember, it's a second order system. It's a second order system, so you're going to have 2 poles, but they're both going to be real. All right, so they're both going to be real if your damping coefficient is greater than 1. If your damping coefficient is exactly to 1, then you're going to have 2 poles that are real, but they're going to be exactly equal. And that'll be a critically damped system. If, on the other hand, your damping coefficient is less than 1, you're going to get an imaginary component in your poles, and that imaginary component is what's going to give you that oscillation. All right, so this here is actually referred to as this is a pole mapping for our system. And so they refer to this as the S-plane, because we're mapping that S, we're mapping where those poles are going to exist, okay, for those frequencies. Now, if you wanted to build a perfect oscillator, you would actually make B go to 0. So if B is 0, then you're just going to have 2 imaginary poles, and they're going to be the conjugate, one is going to be a plus J, the other one's going to be minus J at the same distance. And these, in that case, you would have a perfect oscillating system. All right, so this is a plot that's simply showing you the stability of the system. So if your system has all the poles on the left-hand side of the imaginary axis, then that means the system's stable. If the poles are on the axis, then you're going to have an overdamped system. If the poles have an imaginary component to them, when you take and apply the quadratic formula, if you get a imaginary component out of that, that means your system is going to oscillate. All right, so the steady state, now, if that was all transient response. If we talk about the steady state, we get this value here, as I kind of talked about a little bit earlier, right? In this case, the black line is where our set point is at. but the red line is our actual system. And so what happens is when the system finally settles out and quits moving, so it reaches steady state, it's not matching our set point, and that is called steady state error. Okay, steady state error is when the system has reached its steady state value, it's not changing, yet it's not at our set point. So we want to apply a control system to control the system. And what we need to do when we're trying to control is we got to think about not just the steady state error, which typically we would want to drive to zero, but we also have to keep in mind the idea of our response. Is it going to overshoot? Is it okay if it overshoots? Or do we have to make sure that it doesn't overshoot? So do we have to make it an overdamped response? So we have to keep all this in mind when we're building our controller. Alright, so a lot of times when we're building a control system, you don't want to use a step change. Okay, a step change is what's shown over here on this left graph. And a step change is the immediate jump from one point to another point. And the problem with that is that you're trying to force the system to make drastic changes, which is at a minimal, it's kind of hard on the system. You're making it change as fast as it effectively could. All right, so a lot of times when we're doing control, we use step changes to test the system, to get an idea of how the system is going to work, and to build our controllers, and test our controllers. However, on the actual real system, we don't want to just allow it to just step and jump as fast as it can to the new value. So what we do is we do what's called a ramp or a soak. All right, and the ramp means that when we want to go up to a new set point, we want to move slowly up there. So what we're going to do is we're going to, even though like the operator may have put in a change in set point from say, 0 to 10, so he changed it immediately, our control program actually needs to run up that, so it needs to monitor that, hey, there was a drastic change in set point, but let's just walk it up slowly. So we're going to ramp it up in there. So like over here, a step change, this is kind of like you're sitting at a red light in your car and the light goes green and you just floor it. So you just step on the gas to go as fast as possible. Where the ramp is like, okay, so we step on the gas a little bit and we get the car moving, and as it moves a little bit more, we step on the gas. So we take it easy and we gently increase our speed. All right, and then the soak is just the opposite. It's like you're coming to a red light and coming up to a red light, and you wait till the last minute and slam on the brakes. That would be a step change, and of course that's very hard on your car, hard on your tires, hard on your brakes, right? So we want to do a soak, which means that we're going to, as we're coming up and we see the lights changing to red, we're going to gently slow down and go back down to a lower value or a stop. All right, so the ramp is ramping up in a nice, easy, controlled manner, and the soak is slowing down in a nice, controlled manner. All right, so we already kind of talked about these transfer functions, but let's look at them in just a little bit more detail here. All right, and so with the transfer function, well, we already discussed the steady state and the overshoot and that. But to test the system, we have to excite the system. So a lot of times we use either the step response or what we call a Dirac delta function, which is just a push. All right, so step response is like when you flip a switch and apply a voltage, and that voltage stays constant. It doesn't change once you flip the switch. Where the Dirac delta is just a push. You give it a push and then you let it go. All right, so back to maybe the analogy of pushing somebody on the swing. You give them a push and you let them go for a while, and maybe later you might come along and give them another push. All right, or we could do something else, like we could apply something like a sine wave or something like that. And we do these to our systems to, again, just get an idea of how the system is behaving, and then after we apply our control system, how our control system is behaving. All right, so we talked about all those values here. All right, now a lot of times when we have our initial we have our transfer function, we talk also about an initial condition. Usually the initial condition is 0, meaning that the system is at rest, the system is not moving. But sometimes maybe we want to start by giving the system a push. And so instead of, it's almost like a delta function. So the initial condition, a non-zero initial condition would be like the Dirac delta function pushing it right at time t equals 0. All right. This is just more about the delta function here. All right, so now here is our transfer function. All right, another term for this is actually a differential equation. It's a mathematical term here. This is a differential equation that is showing us how the output is going to respond to the input. Now in this case you can see that we have 1, 0. The 0 is at -3/5, 3 divided by 5. And we also have 3 poles in this system. Using the Octave software here, we could calculate what these poles are by using, I'm going to create a variable called denominator, which is 1, which is the third order, 6, which is the s squared, 2, which is the s term, and 1, which is the omega n squared term. All right, so there's my denominator, and then I'm going to use the roots to find the roots of this polynomial. And so when you look here, you see that it's got one pole, which is at -5, which is real. All right, so anytime you have like a third, fifth, seventh order, you're always going to have at least one real pole, because that real pole is, because if you have an imaginary, anytime you have an imaginary, you're going to have the complex conjugate. So you're going to have a plus I term and a negative I term. All right, so notice that these two poles are exactly the same. Notice that their value is the magnitude is smaller than the magnitude of this pole. So these guys are actually going to dominate, and since they do have an imaginary part, they're going to oscillate. So this is going to be an oscillating system. So the quick Laplace system here takes this what we call the time-dependent response and just replaces derivatives with those s. So it takes it from the time domain to the frequency domain. So remember here, the frequency domain is s represents the frequency. All right, so when we look at our transfer function, and we've kind of already looked at this, we can tell by looking at this transfer function term over here, we can look at the damping coefficient. All right, remember that the term with the s, a single s, represents the friction or the damping in the system. And so if this value is small compared to your natural frequency value, you're going to have a lot of oscillation. All right, so here the damping coefficient is much less than 1, so this system has a lot of oscillation in it. Okay, but the other interesting thing that we can tell from this transfer function is the final value. Notice here, if you let S go to 0, remember S represents a frequency. And so if S is 0, that means DC, direct current, no frequency, no oscillations. So if you let S go to 0, then you end up with 1 divided by 5, which is 0.2. So if you look, the final value, the steady state value of this to a unit step response of 1 is going to be 0.2. If you push this with input of 10, then your final value would be 2. If you pushed it with, say, 20 volts, then the final value would be 4 volts. All right, so 1/5 of whatever you're pushing the system with. So when you look at the transfer function, you can see what the natural frequency is for its oscillations. You can see how much friction is in the system, and you can also very, very quickly see the final value and see how far the final value is going to be off. So we're basically off 80% of what our set point was. So this is an example. Nothing really says it on the slide, but it had a unit step input, which means we pushed it with 1 volt and we got 0.2 volts out. All right, so if we start talking about feedback now, we can apply feedback to the system. When we apply that feedback to the system, we can either change the poles that are there if we do simple proportional feedback, or we could add poles, or we could add zeros, or we could basically do all three. Okay, so we could add a pole, we could add a zero, or we could just kind of shift the poles that are there. Okay, so this is just still talking about the poles. All right, so when we try to push a system, if we're going to control the system, we also have to consider the energy that's being supplied. All right, so the question is, if we're going to push the system, can we push it? How far? So when we're thinking about the control system here, we got to kind of think about how much energy that we have. So I don't know if you've ever watched the Coyote and Roadrunner, but the Coyote is always trying to catch this Roadrunner, and so he's always trying these different things. So you can see, like here on this image, he's sitting on this rocket, and he's trying to light the rocket so that he can catch the Roadrunner. And you know, you can just imagine with him strapped on there right now, he's actually lighting his tail on fire. But if he actually gets this rocket lit and starts going, you know, how's he going to stop it? All right, so you can see how much energy he's trying to put into this control system. So we need to kind of think about that as we look at various control systems. So here is an example of a system that has quite a bit of resistance. Now this was an RLC circuit here, and the open loop circuit has R, and the capacitor was equal to 1 farad, the inductor was equal to 1 Henry, and the resistance is equal to 10 ohms, which means that we have a lot of resistance. So if you look at this black line here, if you look at this black line along here, you can see that the system is over damped. It's very slow. It's rising up and it comes up here and it finally settles out at 5. So now notice in this system my set point was 5, and so the system was a very slow system. It has a lot of resistance. It has a lot of over damping, and so it's a slow response system. So now what I did was I applied proportional gain to that, and I made the gain 1. So I took a gain of 1, and you can see that the system now, it comes up and it's actually slower than it was before. So I closed the loop and now the system is actually slower. But not only is it slower, but look at the steady state error, right? The system was supposed to go up to 5, but with a gain of 1, it's going up to about, I can't quite tell if that's 1.6, 1.7. All right, so that's way off there. So I'm like, okay, well, I'm going to increase my gain. So I increased the gain at 2. Now notice, hey, the system went up much faster and settled out, and it looks like it's pretty much done now. So it took it somewhere around 50 seconds to settle out to its steady state value before, and now it's doing it in about 12 seconds, okay, with a gain of 2. But notice how much more energy that we had to use. So if we look down here, when I pushed it with a gain of 1, I didn't actually use much energy. Okay. When I pushed it with the gain, or just the normal open gain, okay, so when I pushed it with the normal open loop gain, I actually gave it more energy than I did when my gain was 1 here. All right, but now when I pushed it with a gain of 2, it took more energy. It started all the way up at 10 and it just took a lot more energy, but the final error, the final value now is slightly above 2. Okay, or actually looks like quite a bit more than 2. I'm not sure what that value is. I should have printed it out, but you know, you can see that I'm pushing it a lot harder now, right? I'm pushing it harder, which means that I'm using a lot more energy, but I pushed the system so it's closer to the final value, but it's still way away from it, and I'm using more energy than I did by just open loop control. Now, you might be saying, why would we even bother? Well, the thing is, with open loop control, any disturbance, we can't respond to it. But with either of these closed loop controls, either a gain of 1 or a gain of 2, at least we are going to respond to a disturbance in the system because we have that closed loop feedback. Now, on the other hand, though, if we look at this last one, a gain of 4, the gain of 4, the system again responds really fast, right? So it responds and gets to its final value very fast. But it's still nowhere near the set point value. Okay, so I have error. So this is a proportional gain example, and so no matter what I do, I have quite a bit of steady state error. I mean, I could increase my gain more, but you run into an issue, which we're going to talk about next here. But let's see how much energy it's taking now. So now, if you look at this, this is how much energy it's taking it with a gain of 4, right? 4 times as much energy as it was with a gain of 1. And yet, our steady state error is still quite a ways off. Okay. So I want to look at this gain of 4. Okay, and talk about how much energy. All right, so if we go back to this slide thinking about the Roadrunner and thinking about, look at this, he knows that he can't run as fast as a Roadrunner. So he went to the Acme company and ordered this rocket. I suppose if it was nowadays, he'd go to Amazon to order this, but he buys this rocket and straps himself to this rocket to get going. So think about how much energy is in there. Well, here, this is showing the energy that we need okay, for the, this is the energy that our control system needs. Okay, so our control system needs all this energy. And the problem is, though, if you think about a PLC, the analog to digital controllers that we talked about on the PLC, you remember that the PLC, typically it could output a voltage between 0 to 10 volts. Okay, 0 to 10 volts, but this thing is wanting to go all the way up to 20 volts. You just cannot do it. Okay, you're going to have to do like the Coyote and contact Acme company and buy a rocket to get this thing to get that much energy. All right, so you cannot do it. So the red line here that I'm showing down here, this red line is what's going to happen when you try to output this control in your PLC, because the controller cannot go all the way up to 20. Right? The controller is only going to be able to go up to a maximum of 10. So what happens then is that the control goes up to 10 and just sits there, which means that you aren't controlling the response very well. But remember, this is a closed loop system, and so it will respond to disturbances. All right, but it's kind of limited to what it can do, because you're basically maxing out your control. So you're trying to respond to it, but you've maxed out your control. And so, but this is really how much energy you can apply. Right? This is how much energy your system wants, but this is how much energy that the system can supply. So just let me close these. All right, so we need to keep that in mind when we're controlling the system. Now I do have just another example of effectively the same circuit, only I've changed the resistance. All right, so in this case here, I've taken the resistance and I've changed it the resistance so that it's only 1 ohm instead of the 10 ohms in the other circuit. All right, so we only have 1 ohm. So now what you can see that we definitely have some oscillation. Remember, the black was the open loop, and we have some oscillation without applying any control. All right, if I apply some control, so if I come along and I apply control with a gain of 1, we're back to the same thing. We have a huge steady state error, and we actually get more oscillation. All right, and but if I increase that, then, oh, by the way, let's look at our energy while we're at it. So if we look at the energy, this is the energy of our gain of 1 system. Right, so our gain of 1 system here in red, this is how much energy. Remember, energy is your output times time. right? We did the integration lab. This is output times time. That's how much energy that you're using. Now, if you did just an open loop system, right, this would be how much energy you're using. All right, so you're actually, with a gain of 1, we're using less energy than just by pushing the system. And we do have some control. We can respond, but we also have this huge steady state error up here. All right. Now, if we change to a gain of 2, so if we change to a gain of 2, our system responds much faster. We definitely are going to have quite a bit of overshoot. And we also still have this steady state error. Okay. But the amount of energy that we're going to use is up here. Okay, it's below our max possibility of 10. All right, so we are definitely applying some control here, but we have this huge steady state error. But we do have some control. And then finally, then, if we go to gain of 4, okay, our gain of 4, again, the system is responding extremely fast. We're getting even more oscillation. All right, we do have less steady state error, but we're using way more energy than is even available. Right, so remember, the actual available energy was basically to 10 here. All right, so this energy here we have, but the energy up above we don't have. Okay, we can't push that control system there, you know, unless we go buy a rocket to push this system. We can't actually do much with a gain of 4. So our controller might be calculating to give me these responses, but I can't output any more than 10. All right, so we always need to keep in mind our control. And so what's going to happen a lot of times is our controller is going to say, hey, you know, let's attach a rocket and really push this system, but the actual output of our controller or our actuators cannot push it that hard. And so the system is not going to respond as fast as we would like it to, because we just don't have as much energy in our controller to push the system that hard. All right, now if we come over here and look at this, I want to talk a little bit more here about our steady state error. All right, so this steady state error here, when we just do proportional feedback, you really cannot get rid of steady state error. You're going to have quite a bit of steady state error. It's just the nature of proportional feedback. So you do get response, but you also have this steady state error issue. So what do we do about that? Well, we have something called the PID controller. All right, and so you can do just PI control. You can just do P control. P means proportional. Okay, proportional is what I was showing here. These are just simple proportional controllers. And as you increase the gain with a proportional controller, you get a couple of things happening. Number one, you get the system to respond faster. All right, you get the steady state error to decrease. So as you increase your gain, as your gain increases, the steady state error decreases, and the response it responds faster, but you also will tend to get more oscillation and more overshoot, okay, with proportional control. All right, so then what we can do is we can integrate. We already did like the integrator lab for integrating just to find energy, But what integration does is it basically adds, if we think about the transfer function, it adds one pole at zero frequency, or DC. And what that means is it will, if there is error in the system, this will keep pushing the system until the error goes to zero, or you saturate your control output. Right? So remember, we were just kind of looking at it, that over here, right here, this bit here is, I can't push the system this hard because my control system saturates. So if you have enough ability in your control system, adding an integrator to your controller will drive the error to zero. Okay, so what we like about integration is it drives the error to zero. All right, now the D stands for differentiate, or derivative. All right, and so what this does is this adds a zero to the system, and it actually ends up adding 2 zeros to the system when you do all the math. When you do a complete, if you do a complete PID, then you're going to add a 0 and a pole to, or excuse me, you're going to add one pole. You're actually going to add 2 zeros. If you do all 3 of these, you'll end up with adding 2 zeros. But what this does to the system is it predicts changes, or it tries to interpret and predict how the system is going to change and control it, and basically it tries to decrease oscillations. However, if you increase the gain for your derivative piece too much, it's very easy to drive the system unstable. Okay, so but it will tend to a derivative looks at how fast the system is changing. So a PID controller, the derivative piece will try to react to the changes in the system. Okay. Now you can do just proportional, as I was, as we talked about actually last time, simple proportional, or you could do a PI controller. So you could add just some proportional and integration, or you could do just a PD and do, try to control how fast it responds to changes, or you could do the full PID. Now, people typically don't do a proportional derivative. They either do a PI or they may do a PID. All right, so remember that the key component of the integrator piece is the fact that if you have enough energy in your system, you can drive your steady state error to 0. All right, but when you do these controls, you have to be careful that you're not trying to push them harder than they can go, and you also need to be careful because you can push them into instability. So even though the system is stable, if you add a controller, you could drive it unstable.